that we put together recently. Okay. So now what I want to do for the rest of today is I want to just work through a set of problems, have you guys help me answer them and see if we can work through them. Okay, so this first one is an example that you'll find in your textbook. And here's what it says. It says in experiment 12, which is listed in your experiment, touching one metal sphere with a charged plastic rod causes the second metal sphere to become charged with the same type of charge as the rod. How does this happen, essentially? Okay, so what is this experiment? So this experiment was I had two metal spheres that were in physical contact with one another. They were conductors. And then I'm going to take a rod here that has some excess positive charge, and I'm going to touch it down to this sphere. And what I observe after I touch that, right, if I then observe those two spheres after I touch that rod to the two spheres, I find that they are both positively charged. Okay. So what does this tell us about charges and how they play with a conductor? Can anyone tell us what this observation, what this experiment reveals about charges and conductors? If you want to type it in the chat, feel free to do that. Charges flow through the conductive objects. That's exactly right. We put the positive charge at one place on the conductive sphere, and so that charge distributed itself, right? The charges in the conductor rearrange themselves, right? So this is a good demonstration that there's conductivity. Those charges can move themselves around inside of this conductor. So how would this have been different if instead of these being metal spheres, they had been plastic spheres, insulating spheres, right? If they had been plastic and I touched the positive charge here, insulators don't allow the charges to move around. So if I were to then separate those two objects, I would have that all those charges were still stuck on the left-hand sphere, and then I would still have zero charge over on this object. So I can do this experiment with different materials and understand this idea of insulator versus conductor. The conductor really allows the charges to flow around, and not only allows it, but if there's charge on a conductor, it will distribute itself uniformly across that entire metal object. And we think about a metal object as any pieces of conductor that are in physical contact with one another. Okay. What about this problem? So I'm going to open up a poll here in a second and let you guys all pick your answer. But here I've hung a positive charge from a thin string, and I've brought a rod nearby. And we can see that that object that's hanging there is being attracted to that rod. What can we say about the charge on that rod? Is it positive, negative? Is it neutral? Or could it be some combination of the two? Could it be positive and neutral, or could it be negative and neutral? I'm going to launch a poll here. And I would like you all to take about 30 seconds to select your answer. Okay, I'm going to end the poll. So the majority of you selected that it could be either negative or neutral. And that's the correct answer here, right? If this was a negatively charged rod, there would certainly be attraction between the dissimilar charges. If this was a neutral rod, it would have a mix of positive and negatives, but we know that those positive and negative charges would separate themselves as much as possible. Okay. So it would also be attracted, right? The negative charges, sorry about that, the negative charges would be pulled as close as possible to that positive charge. Let's think about this example here. Won't there be, oh, sorry, there's a comment here. So a couple questions in the chat here. So I hear some people saying the conductor and contact act as one system. Yeah, so when there's two pieces of conductor that are making physical contact, you can just think of that being like one common conductor, one funny shaped piece of conductor. And then there's another question, wouldn't there be slight separation among the charges, right? That's exactly right here, that for this neutral object, the negative charges are going to separate themselves from the positive charges and get a little bit closer to that positive charge, and that's why I'm going to get that net attractive force, because the negative charges will be slightly closer. What about this example here? What if I have two metal spheres, two conducting spheres, and I'm going to bring a positive rod near those conducting spheres. And I'm not going to touch that rod to the metal spheres. I'm just going to bring it nearby. And then I'm going to take the rod and I'm going to move it far away from those spheres, and then I'm going to separate the two spheres. So I bring the rod nearby, remove the rod without making physical contact to the spheres, and then separate them, and I'm going to measure the charge on each object. So what will I find? How will the charges be? Okay, let me relaunch this poll. Take a second to decide. Will object 1 be positive and object 2? Will one be positive and the other one negative? Will they both be non-charged? Okay, I'm going to end the poll. So most of you said that they end up being neutral. Okay, that's absolutely correct. What happens here when I bring this positive rod near these conducting spheres? The negative charges are going to be attracted over here, leaving the object 2 to be more positively charged. But as soon as I remove this rod from the system, those charges in the sphere are going to redistribute themselves, right? I'm going to end up getting the negative charges flowing back over this, and the positive charges are going to flow back around, and they're going to redistribute to leave me with something where I have 0 charge on each one, right? So when the rod is nearby, it polarizes that conductor, it pulls the charges apart. As soon as I take the rod away, those charges remix and I end up with a neutral object. So then when I separate the spheres, I have 2 neutral spheres in the end. What if I change the order? What if I bring the rod nearby, then I separate the 2 objects, and then I remove the charge rod? What will the charge look like on the 2 spheres? Go ahead and provide your answer. Okay. So most of you selected that object 1 would be negatively charged and object 2 would be positively charged. That's the right answer, right? I bring this rod nearby. It's going to pull the negative charges closer to the positive charge. It's going to leave object 2 positively charged. If then I keep that object in place and I separate them, right? Negative charge over here, positive charge over here. Now they're no longer physically contacting one another. And then I remove the rod. What's going to happen? Well, the negative charges are going to redistribute themselves uniformly through this conductor. These extra positive charges will, right, this side will be uniformly distributed, but the electric charges, the extra negative charge on object 1 can't make its way back to object 2 because there's now a gap between the 2. Okay? So I end up with that object 1 is negatively charged, object 2 is positively charged. Somebody in the chat is asking, what happens if the charged rod touches one of the conductors? Okay. What's going to happen then if the charge rod touches one of the conductors? Any ideas? Well, if I make physical contact, let's go back to say, let's just draw it here. If I have my two conducting spheres here touching, and I take my rod with positive charge, and I make physical contact to the conductors. Now what's going to happen? Now that charge is going to transfer off of the rod because I made physical contact. It has a path to move onto the conductor. And that positive charge is going to say I was able to get all the excess positive charge off the rod. The rod will then be neutral, right? Or some amount of charge will be transferred. And if I move the rod away, now that positive charge will redistribute itself and I'll end up with two positively charged objects. All right. What about this example? Based on the last experiment, where the two spheres, where we charge the two spheres by induction, what can we conclude from this experiment about the mobility of the charges in a conductor? Which are the type of charges that are moving around in the system? Is it just the negative charges? Is it just the positive charges? Is it both the charge moving around? Or can we not say from this experiment? So let me relaunch the poll. What do you guys think? The fact that we see these two spheres becoming charged due to an external charged object coming nearby, what does that tell me about the mobility of the charges? Okay, let's go ahead and end the poll. So a lot of you thought that both the positive and the charges move. Another good fraction of you thought that only the negative charges move. Okay. Well, let's see here. Let's imagine all three scenarios and see what would happen here. Okay. Let me just get a blank page here. So let me imagine that I have the two spheres touching one another, and I bring my positive charge nearby. It's going to attract, so let's imagine before I bring that rod nearby, let's say I have my positive and my negative charges sort of uniformly distributed through these conductors, right? I have some neutral object and the charges are just spread out in some equal way so that I have a set of neutral objects, right? Now I bring this rod nearby. What's going to happen? Well, let's imagine one scenario where it's only the negative charges that are allowed to move and the positive charges have to stay in place. What'll happen? All these negative charges will move to the left. They'll be attracted to that positive external charge, right? They'll all start moving in this direction. The ones over here too will be attracted and they'll start moving in this direction. And even if the positive charges are staying put, what do I get? After I wait a while, I'll end up with a bunch of negative charges on this side and some uniform positive charges still spread around in these two spheres, right? Let's assume they're still connected, right? And so I'll see that I'll end up with a negatively charged, right? There'll be a lot of negative charge over on this guy. And I'll end up with a net negative charge on this side and a net positive charge on this side. If I play that same game now, bring the positive charge nearby, I have my charges uniformly distributed through this thing, some positive, some negative, spread sort of equally through this system. Now let's assume it's the positive charges that are mobile and the negative charges stay put. What would happen? Well, all these positive charges will be repelled by this external positive charge, and they'll all get smushed to this side here. They're all going to head this way, and the negative charges will stay put, right? And I'll end up with two spheres that'll have a bunch of positive charged all pushed towards this far end, right? All the positive charges and some negative charges sprinkled around, but there will be more negative charge left on the left-hand side. So again, I'll end up with a negatively charged sphere and a positively charged sphere. And if it were both of the charges that were mobile, right, what would happen? Well, the negative charges would be free to move in the material and they would all be attracted to this external positive rod, and the positive charges would be, oh dear. Sorry about that, my browser just crashed. And the positive charges were, the positive charges would be free to move away, and I would end up with a distribution that looks like this, where the negative charges would all be smushed to the left, positive charges would all be smushed to the right. And right, so we see that in all three of those cases, we end up with negative charge to the left, positive charge to the right. We end up polarizing these spheres independent of what kind of charge moves. As long as some of the charges move around, we get this polarization effect. Now we know that it's the negative charges, the electrons, that are the ones that are free to move inside of a conductor, but that comes from understanding the details about the atomic structure, the fact that there's a heavy nucleus that holds the positive charge and these light, loosely bound electrons that can easily be removed or moved further away from that positive charge in a conductor. So we know that in reality, it's the negative charges in a conductor that are freely moving around inside of the material. But that doesn't come from this kind of simple polarization experiment. It comes from some other detailed experiments to understand the atomic structure of the materials. What about this experiment? I have 3 identical spheres, right? They're all conductive spheres that have different initial charges set up on them. Sphere P has positive 4 nanocoulombs of charge, sphere Q has negative 2 nanocoulombs of charge, and sphere R has negative 1 nanocoulomb of charge. And then I'm going to perform a series of operations. I'm going to take sphere P, I'm going to touch it, make physical contact between P and Q, and then I'm going to separate those 2 spheres, and I'm going to take Q afterwards and make physical contact with R, and then re-separate them. And I want to know, what charge am I left with on sphere R after these operations? Okay. You can see your choices, A, B, and C here. I'm going to open up the poll. So take maybe up to a minute to answer this one if you need it. You should be seeing the poll result now. The poll. Okay, I'm going to give you about 20 more seconds. Okay. A few last answers coming in. Okay, I'm going to end the poll. The majority thought that it would end up with 0 charge on sphere R. Okay, let's see if that's correct. The first thing I do is I take P and place it in contact with Q, something like this. This guy was positive 4, this guy was negative 2, right? What's the net charge on this thing? It's 4 minus 2, so I have positive 2 nanocoulombs of charge on that, just that large object, right? That collection of conductor that I have there, those 2 spheres placed together. How will the charge be, sorry, that's a positive 2 nanocoulomb. How will that charge be distributed on those 2 conductors? Well, it's a conductor, so the charge distributes itself uniformly. That means I have to have a positive 1 nanocoulomb of charge on this side of the sphere and positive 1 on this side, right? I have 2 identical spheres and the charge is uniformly distributed, so half the charge has to be on each side of the system. So now I see that object Q, after I touch those 2 objects together, ends up being a sphere with 1 coulomb of charge on it. Now I'm going to take that object and bring it over here and make physical contact with R. So now I'm going to touch a positive 1 nanocoulomb charge to a negative 1 nanocoulomb of charge. That means I have a net charge of 0 coulombs on the system. How will the charge be distributed? It's a conductor, so it's distributed uniformly. So each of them end up with 0 coulombs of charge on them. So in the end, I end up that the charge on sphere R is going to be 0 nanocoulombs.